Good afternoon, everyone. Hopefully we got folks coming in here. Again, I'd like to welcome you to the Office of the Chief Scientist Science Seminar Series. My name is Jonathan Thompson, and I'm the Chief Scientist for the Government of Alberta and your host for today's seminar. Dr. Paul, our regular host, is away today attending a water-related workshop. However, on behalf of the Office of the Chief Scientist, I want to welcome everyone to today's special event. In the spirit of reconciliation, I would like to respectfully acknowledge that today we're broadcasting throughout Alberta and beyond on the traditional lands and gathering places for Treaties 4, 6, 7, 8, and 10, and the homeland of the Métis peoples. So wherever you find yourself today, I encourage you to recognize and acknowledge the shared relationship that First Nation, Inuit, and Métis people have with the land on which we all live, work, and learn. In keeping with the tradition of gathering, these science seminars provide an opportunity for us to get together to exchange knowledge on relevant and interesting science happening across Alberta or more broadly across the country in an open and sharing environment. The hope is that through our dialogue today, we're able to improve our awareness and understanding and put this knowledge into practice to help support evidence-informed decision-making wherever that occurs. To help maintain our call quality today, your video and your audio has been disabled. However, you can enter your questions or comments at any time during or after the presentation via the chat function in Microsoft Teams. After the presentation has concluded, we will address the questions in the order that they were received. So today, I'm very pleased to introduce our distinguished speaker and EPA Science Advisory Panel member, Dr. Irena Creed, who will be presenting on harnessing the power of wetlands, nature's blueprint for climate solutions. Dr. Creed is a professor in the Department of Physical and Environmental Sciences at the University of Toronto. She is a former Canadian Research Chair in Watershed Sciences and has been elected as a Fellow of the Royal Society of Canada and the American Geophysical Union. She is an internationally renowned watershed and wetland ecosystem scientist who's received numerous recognitions for her work, including the Royal Society of Canada's Bancroft Award, an honorary doctorate of agricultural sciences from the Swedish University of Agricultural Sciences, a visiting female professorship at Umeå University in Sweden, and the distinguished Wallenberg Professorship from the Royal Swedish Academy of Agriculture and Forestry. Her research interests are quite diverse and include watershed sciences, hydrology, ecosystem services, climate change, and particularly the science policy interface, among another of important topics. With that, I would like to welcome Dr. Creed to our science seminar series. So over to you, Irena.
Thank you for that very warm introduction, and good afternoon to everybody. It is an absolute privilege for me to be able to speak on this topic that I'm passionate about to you today. I'm going to start with giving you my key message. The key message is that wetlands play a pivotal role as natural climate solutions, contributing to carbon sequestration and greenhouse gas emission reductions. And my position is that their protection and restoration are crucial for Canada to meet its Paris Agreement target of a 30% reduction in greenhouse gas emissions below 2005 levels by 2030. And for the past decade, myself and my incredible collaborative network have been focused on integrating wetlands, providing the evidence base for wetlands to be integrated into the greenhouse gas inventory reporting by addressing some of the uncertainties in the carbon benefits of wetlands. Now, there are 5 key points that I want to share with you. And the first point is that Canada's commitment to cut greenhouse gas emissions by 30% below 2005 levels by 2030 hinges significantly on natural climate solutions. As most of you are aware, every nation that signed the Paris Agreement must submit a national greenhouse gas inventory report each year. And Canada has the Canadian Net Zero Emissions Accountability Act to give us legislation for our monitoring program. And I want to share with you some of Canada's climate targets. In 2005, our emissions totaled 730 megatons CO2 equivalents. If we were to achieve a minus 30% climate target from that 2005 level, we would need to reduce it to 511 megatons CO2 equivalents by 2030. However, the climate crisis is ongoing, and countries have responded by creating new targets that are even lower. And Canada has now committed to minus 40 to minus 45% from those original 2005 levels, meaning our target for 2030 is now 401 to 438 megatons CO2 equivalents. Now, nature plays an important role in climate mitigation, and I just want to give you a formal definition of what natural climate solutions are first. These are actions to protect, conserve, and restore nature to store carbon and reduce greenhouse gas emissions. And scientists estimate that on a global scale, up to 10 gigatons CO2 per year can be removed from the atmosphere by nature. This includes two categories. One is the avoided emissions, which is what is accounted for if we protect intact lands. And that includes protecting our forests, protecting wetlands, and protecting grasslands. But there is also another category of creating enhanced sinks, and that is through managing lands, but also restoring native cover. And in particular, I'm interested in today's presentation focusing on the protection of wetlands and the restoration of wetlands. Now, these are global estimates, and now I want to turn, what are the Canadian estimates? In a recent paper that was published in Science Advances, basically thought leaders across Canada came together to estimate what natural climate solutions targets could be achieved through nature. And that was 78.2 megatons CO2 equivalents annually by the year 2030. This represents 18 to 20% of our total commitment. Hence, my first statement is that natural climate solutions are critical for us to achieve our commitments to the Paris Agreement. Let's explore a little bit within Canada how that 78.2 megatons CO2 equivalent plays out. In this plot, you'll see the protect, the manage, and the restore, and you will see the various different ecosystems, forests, grasslands, and shelter beds, and wetlands. And what I want to point out is that in protection, about 30 megatons carbon dioxide equivalents per year. In management, even more at 44 megatons carbon equivalents per year. And in restoration, it's 3.8 megatons carbon dioxide per year. And what I want to really focus on is the disproportionate role that wetlands can play in achieving these greenhouse gas emission targets. In terms of protecting, 13.5 is the total amount compared to only 3.8 for forests and 12.7 for grasslands and shelter beds. And in the restoration, it's 2.2 megatons carbon dioxide per equivalents per year, compared to only 0.3 for restoring forests and 1.3 for restoring agricultural and grasslands. And so this really puts a spotlight on the special role that wetlands can play in Canada meeting its providing natural climate solutions. So the federal government has in 2022 outlined what its financial commitments would be to put into place these natural climate solutions. And of these, 3.2 billion is to meet the government's goal of planting 2 billion trees, 631 million to protect and restore grasslands and wetlands, and 98 million to establish a new natural climate solutions for agriculture fund. And that fund is doing boots on the ground work for restoration, but it is also looking at projecting the success of some of the efforts that with the tree planting and the protection of and restoration of grasslands and wetlands would have into the future. So bottom line, there's a lot of money on the table, and it's important to make sure that those monies are spent effectively and efficiently. So my second point that I want to make is that a change in the classification of wetlands is needed for wetlands to be included in national greenhouse gas inventory reports. Wetlands can only be included in the national accounting if they're considered managed. And so the question I would say, are wetlands considered unmanaged or managed in Canada? And in Canada, all wetlands are considered unmanaged. I just wanted to give you a comparison to the United States. And in the US, most wetlands, except for some small areas in Alaska and around transportation networks, are considered managed. And so Canada unmanaged, United States managed, yet both countries have yet to formally put the wetlands into their national greenhouse gas inventory reporting. Recently, this past summer, some members of the network joined forces with people from the United States in Washington, D.C. to talk about what would be the pathway, what would be the road to getting the wetlands included into the national greenhouse gas inventory reports. And we are starting to define that and make efforts to move forward in that regard. In preparation for that, the federal government asked us to consider what it would take, what information we should have if we were to reclassify wetlands from unmanaged to managed. And we conducted a survey of experts, not only in Canada, but also included some from the United States and Europe, into considering what would it take to include wetlands into national greenhouse gas inventory reports. And the four following points were made clear. The first one is managed seems to be a bad term if it needs to be included in a greenhouse gas inventory report. And it has a bias to that. And yet management practices can lead to either positive or negative outcomes in terms of carbon sequestration and greenhouse gas flux mitigation. And so we really wanted to show that it's not just a negative and looking at what the emissions are, but it could be a positive. The second point is that human activity must be accounted for across the entire contributing catchment area to the wetland itself, as well as to its downstream waters. Thus, upslope, wetland, and downslope carbon must be tracked. And of course, we need some tools in order to be able to do that. Further, you know that I talked about it's either unmanaged or managed, and mostly all wetlands are either managed or unmanaged in Canada and the US. But we would argue that the type, the magnitude, and the intensity of human activity must be considered. And further, we might want to consider the transient versus permanent nature of management actions when looking at what should be included in the national greenhouse gas inventory reports. So if Canada decides to include wetlands in their reports, there are 4 dates that need to be considered, and therefore there is an urgent need for data to support these 4 dates. First of all, there's the reference year, which is the internationally recognized reference year from the Kyoto Protocol. That is the benchmark for emissions reporting. That is 1990. 20 years before that international reference year, they take the amount of greenhouse gases from that year and assume that that's the residual emissions for when they look at the 1990 years. So those are emissions that happened before any actions were taken. 2005 is the year for Canada's Paris Agreement commitments, and that's a benchmark that we have mentioned before. And then starting in 2020, when a lot of us have started to work on this, we've been trying to work to get data that we could monitor that progress on an annual basis. Now we have the term of being managed or unmanaged. We've talked about the specific years, and obviously that we need data in order to be able to have them included into the national reports, but we also need principles. And a recent paper in Nature Communications talks about a principled approach for inclusion of wetlands as natural climate solutions. In this spoke and hub and spoke wheel that is shown here, there are two types of principles. One of them are foundational, and that's the outer rim. And then the second one are operational, and those are the spokes inside of the wheel. And so just briefly, the foundational principles must be that they are nature-based, they're sustainable, they're additional, they're measurable, and they are equitable. As scientists, we are really focusing on the measurable part, and that's really the focus of my seminar today. And under these, you could see that to be measurable, we need to use the CO2 equivalent metric. We need to account conservatively. We need to report uncertainty, and we need to avoid double accounting. So when we started this network of collaborations, we realized that we needed to really pull and synthesize a lot of data together, because how much do we really know about the climate benefits of protected and restored wetlands, whereas we do have that national accounting of what could be protected, managed, or restored. That's at a high level. And what we need is information at a provincial level, at a municipal level, and down to individual wetlands. And so my third point is to talk about the need for authoritative estimates of both where the wetlands are, and that includes the number and size, and as well the rates of carbon sequestration and greenhouse gas fluxes to the atmosphere, both needed for this type of greenhouse gas inventory reporting. I know that there are major efforts underway within the Office of the Chief Scientist on creating some of those wetland inventories. And I know that that is not only something that Alberta's interested in, but in many jurisdictions I speak to people around the world, getting really good wetland inventories is essential. And I'm going to talk, I'm not going to talk about the efforts I've made with respect to that. If anyone's interested, they can reach out to me subsequently. But really what I want to focus on here is about the carbon sequestration and greenhouse gas fluxes. And so if we're going to be putting information, for example, the province of Alberta into a greenhouse gas inventory, how many wetlands are there and what are their carbon storage and greenhouse gas mitigation potential? And so this is where we have now formed an international research network to try to provide that information to governments. The project is called the Wetlands as Nature-Based Solutions, Quantifying Carbon Capture Potential While Building a Stronger Green Economy. Our vision is to position Canada as a global leader in leveraging wetlands as nature-based solutions, contributing to climate stabilization, while safeguarding wetland ecosystem benefits for a sustainable future. And our mission is to deliver science-based methodologies for assessing and maximizing the climate benefits of wetlands in agricultural landscapes. I want to point out that there are several research networks ongoing in parallel. There is also a major network led by Maria Strack from the University of Waterloo, which is one focusing on the boreal wetlands, the peatland wetlands. And we do interact and share knowledge so that we can both benefit from our expertise and experience. I just want to share with you that this international research network number is growing, involves scientists from coast to coast in Canada, as well as the United States and in Europe, and in particular Sweden. And it also involves leaders of institutes like the Global Institute of Water Security and Food Security in Canada, as well as academic institutions. It is an interdisciplinary team. We have people who are natural scientists and engineers, as well as sociologists and economists. So what is our research focus? We've been mandated to look at agricultural landscapes, most of which are in southern Canada. And you can see from Stats Canada, this map area, all the areas in green are the agricultural landscapes. But my training is as a watershed scientist, and so we do look at a lot of the work for the entire Lake Winnipeg watershed, as well as the Great Lakes St. Lawrence River watershed as well. From a Canadian federal government perspective, a priority area for inclusion of wetlands into the National Greenhouse Gas Inventory Report is the prairie pothole region. And so today I'm going to really focus on what advances we've made for that region in particular. So just for your information, when we do these National Greenhouse Gas Inventory reports, the government would like us to report them on what are these units, homogeneous units within the area. And those units are based on the soil landscape of Canada's soil polygons. And so some of the information that I'm going to share with you is going to be based on those polygons, because that makes our research more efficiently streamlined with the needs of governments, and that's what we want to do. So recently, we were able to use the wetland inventory data that we generated. It's done on an annual basis, and it's from 1984 to present. And we looked at the 1990 to 2020 wetland drainage rates. And so this is the number of wetlands that were drained within that priority prairie pothole region. And as you can see, the drainage rates are ongoing. In some areas of this region, they're going faster than others. The units here are not linear, so the pale blue is basically about one wetland would be lost 0.01 wetland per year, so you can extrapolate that to how many over a decade. But if you go down in the hot zones, they're looking at about up to 67 wetlands lost per year in number. And often these are the small wetlands on the landscape. This is the same information, but it's given to you as an area basis. And again, showing where the hot spots of loss are over the 30-year period. But of course, wetland loss has been ongoing since settlement by Western settlements. And it's really difficult sometimes to get what the natural landscape would be, what the benchmark is before that settlement, but at least we are now able to do that since 1990 forward. So then the question comes, that we have the inventory and we can see the drainage loss, and how much carbon benefit is there on the wetlands in the agricultural landscapes of this region? What is there now and what could there be? And so I want to look at this from two lenses, one from the protection and one from the restoration lens. So first of all, from the protection lens, how can we estimate the net carbon sequestration potential in intact wetlands? And so for this, we look at a very simple carbon cycle. We know that wetlands are very important carbon bioreactors. They store carbon, but they also emit it. And that when they emit it, those are the greenhouse gases of CO2 and methane. Some of you may be wondering, well, what about nitrous oxide, another important and potent greenhouse gas? Our evidence of the team suggests that nitrous oxide is not as important a greenhouse gas in this landscape, but CO2 and methane are. Now, there's been a lot of debate, not just in Canada, but internationally, and particularly in Northern Europe, about the use of wetlands as natural climate solutions, because they basically act as a double-edged sword. Why? Because they can remove CO2 from the atmosphere, but they can produce a more potent greenhouse gas, methane, into the atmosphere. And so I just want to talk about that for a moment. So we know that greenhouse gases have different global warming potentials, and IPCC, the International Panel for Climate Change, will report them using the GWP, the global warming potential, which are estimates over a 100-year time horizon. And so when you look at that for CO2, it's CO2 equivalent. Therefore, that's your benchmark of one unit. But for every one of CO2, you have 28 global warming potential for methane and 265 times the CO2 for nitrous oxide. And so we appreciate the big concern about methane from wetlands. Very recently, my PhD student and I, together with Pascal Badeau, published this article on new perspectives on temperate inland wetlands as natural climate solutions under different CO2 equivalent metrics. The key message here is that the GWP really gives overemphasis on the global warming potential of methane because it assumes it is constant over a 100-year period, when methane is actually a very short-lived gas. And so in this important paper, we found that when we factor in the duration that the gases are in the atmosphere, that if we were to protect wetlands, there would be an immediate net cooling that aligns with the Paris Agreement. And if we were to restore wetlands, and imagine you're taking a wetland and putting water on that, and you might be creating an environment where methane will start, we found that even with restoration of wetlands, there was an immediate reduced warming compared to drained wetlands, with net cooling occurring not immediately, but over longer time scales, such as 100 years. So the message here is that protection, you get immediate benefit. Restoration, you get not a net cooling, but still a benefit due to reduced warming. But over 100 years, we can start having that net cooling effect. And so the data I'm going to show to you next considers the net CO2 sequestration. So it considers CO2, but not the different warming potential of methane. And I just want to let you know that we're currently working on being able to factor that in explicitly in the continued work of the same PhD student. So now let's look at what that net carbon sequestration potential is. We analyzed 30 wetlands and 90 sediment cores across the prairie pothole region, as well as some parts of Ontario. And what we show here are the results for 21 of the intact wetlands. You can see what the mean carbon sequestration rate is of 0.68. You can also see that there's significant standard deviation around that. You see that both in the numbers, but also in that kind of bimodal distribution of the plot. So this is the challenge. If we're going to come up with numbers and estimates of the carbon capture potential, and you have so much variability, how do we account for that variability? And so we pulled together experts and went to the literature and produced this paper that is under review that looks at the system controls on carbon sequestration rates. And this is really inspired by Jenny, who was in the 1940s, a soil scientist who talked about the state factors that control soil formation processes. And he included biota, time, parent material, topography, and climate. And what we did was customize that conceptual framing to look at the interactive controls, the indirect controls, and the direct controls on the wetland carbon cycle. And so the direct controls include the carbon quantity, the carbon quality, soil properties, including bulk density, cation exchange capacity, the aggregate reactivity, the redox potential, and of course, temperature. Now you'll notice that I've highlighted in red some of the proxies that we can use using satellite remote sensing to be able to predict these direct control effects on the wetland carbon cycle. Now, when Jenny first came up with this conceptual framing, it was before the era that we call the Anthropocene, which is in around 1960s. And of course, human activity has had a major effect on the wetland carbon cycle, including through their cropping systems, the tillage and livestock, fertilizers, wind and runoff erosion, drainage and restoration, as well as salt application, although notably salt is not a problem in the prairies, but it is a problem in many other parts of North America. And so here too, we looked at generating a satellite remotely sense-based approach for predicting the human activity effects on the wetland carbon cycle. And I just want to show that using artificial intelligence, we were able to look on the left is which variable is the most important. It's called a variable importance plot. And we see human impact index was the number one important variable in predicting how much the carbon sequestration rate would be. After that, it was the soil properties, but there was also the inundation probability and the productivity indicated by the integrated normalized difference vegetation index, as well as land surface temperature. The good news, lots of complexity here, lots of nonlinear relationships between some of these variables and the carbon sequestration rate. But when we put it together through the machine learning random forest model, we are able to explain 92% of the variation in carbon sequestration rates. And so what that means is we feel that we were able to reduce the uncertainty of estimates of those net carbon sequestration rates. Currently, members of my team are looking to do the same type of work for predicting the CO2 and methane emission rates so that we can look at all aspects of carbon within wetlands. So that was about intact wetlands. I now want to turn to wetland restoration. How can we estimate the net carbon sequestration potential in restored wetlands? And so here, once again, we benefited from all the work that has been done, both within the prairie pothole region, but this photo sequence is one from Ontario. And what we did was establish a chronosequence of restored wetlands to monitor the changes in the rates of carbon sequestration with restoration age. On the left, you see it's drained, and then we basically took what we were given, so to speak. We went to the inventory of wetlands of different restoration ages, and what we were able to do in this time sequence in Ontario was drained 50-year, 15-year, 25-year, 40-year, and what was considered intact. And if you look from the photos from left to right, you may notice that there's a change not only of the wetland itself in terms of the amount and permanence of water, but also surrounding the wetland in terms of the riparian structure. I want to point out that these were considered easy to restore wetlands. They were relatively small. They had no hydrologic inflow or outflow, drained by a drainage ditch and restored simply by plugging that ditch. We then took those cores and then we dated them, and this was with collaboration with David Lobb from the University of Manitoba, and we were able to estimate the annual organic carbon sequestration rate. So here are some of our findings. This is now combining two chronosequences, one based in Alberta with the one in Ontario. Remarkably, it's really hard to get these chronosequences, and so we were able to pull together all the data that were available. Despite the challenge in getting the data, it's interesting to see that this is the total accumulated carbon stock with age over that whole sequence. And so now we're able to get it from the earliest one we had was about 4 years since restoration up to about 40 years. Now that's the cumulative. I want to now look at what it would be on an annual basis. So this is the change in carbon sequestration rate, and it is the change from the restored wetland to the pre-disturbance, pre-drainage state. And so when you start in the origin, the 0, means there's nothing, no difference compared to before you started to restore it. But what you see in the first 5-year period is a remarkable rise. And then you see that it starts to decline after that, and that after about 20 years, the rate returns to a pre-drainage period. This led us to think about a lot about what happens when you restore wetlands. And some of the conceptual thinking is that if you have an intact wetland, it's really nutrient limited. You will have a relatively low compared to restoration rate of carbon accumulation because nutrients may be limited. When you drain that wetland, it becomes water limited. So you have a low rate of carbon accumulation because there's oxygenated soils. But when you go through the early restored period, where it's neither nutrient or water limited, you get a really high rate of carbon accumulation. After a period of about 5, maybe 10 years, that rate declines, and then you start seeing still well above the pre-drainage condition, but it does start to decline because we think that nutrients start to become limited, and then finally it returns to that baseline. When you look at something like this as a scientist, you start wondering, can I manipulate that curve? And the answer is yes. We can amplify the carbon benefits. And so we did a review of the management interventions that can enhance carbon sequestration rates. And they include things like water, maintaining the inundation status, maintaining a stable wetland water level. They also include vegetation, where we can restore native wetland vegetation around the wetland. It includes soils. We can minimize soil disturbance, but we can also apply soil amendments. And this is an area of new investigation that we are anxiously hoping to do in the future, where we can apply things like biochar to look at if we can enhance the carbon sequestration potential. And finally, nutrients. We can establish buffers and we can optimize fertilizer use. So my fourth point is, now that we've shown that it is possible to have authoritative estimates of carbon sequestration, and in the time limitation I had, we have done further modeling on the greenhouse gas fluxes, and we feel very confident in being able to predict those as well. But now we think we need practical tools, tools that people on the ground can use. And this is what I'm calling the wetland greenhouse gas calculator, or wetland carbon calculator, so that we can predict the impact of protection and restoration on the wetlands carbon balance. And so the question here is, how can we estimate what that climate mitigation potential of wetlands will be in a quantifiable, repeatable, avoid double counting approach? And so this is relatively new. We're currently designing a practical tool for estimating the wetland climate mitigation potential. And again, remember those operational principles of measurable. We will use the CO2 equivalent metric. We will account conservatively. We will report uncertainty. Now, the issue is about the double accounting. And so this is one where we would have to be mindful of the wetland in context to the working landscape it exists and what happens upstream and downstream from that. And so we are working now on being able to model the carbon flows into and out of wetlands so that we can avoid that double accounting. And so work with Amelie Ali from University of British Columbia will be looking at identifying the static hydrologic connection of wetlands in agricultural landscapes, how they change over time, their dynamics, how they expand and contract to connect to each other as well as to the hydrologic network. And then we want to explore the effects of wetland draining and restoring on those connections, and then predict the upstream wetland, downstream carbon flows. This will be essential in terms of being able to avoid the double counting, but also to give the carbon benefits to who is responsible for reducing greenhouse gas emissions and enhancing carbon storage. And so when we look at this, we'll be looking at scalable models that factor upstream and downstream. And because wind erosion is also important, eventually we would like to include upwind and downwind carbon flows using a combination of GIS, remote sensing, and modeling. Now, this takes me to my final point, which is, how do we incentivize the protection and restoring of wetlands? As you saw earlier in the seminar, the wetland number and area of drainage is ongoing. And so how can we incentivize to see a reversal in that those types of behaviors? So what social and economic factors should be considered to incentivize wetlands as natural climate solutions? Other members of our network include sociologists and economists, and this is some of the you're the first to see these results of a survey that was conducted. This is focused on the prairie pothole region, asking the question, why do farmers drain wetlands? And I just want to acknowledge the work of John Pattison Williams from the University of Alberta, Pat Lloyd-Smith from University of Saskatchewan, as well as Roy Brower from University of Waterloo. And in this, you will see that it's not purely, it is largely economic pressures on why farmers drain wetlands. It's the nuisance cost. It's the lost revenue due to missed farmable areas. It's the overlap costs of added expenditures to avoid the wetland, and the adjacency cost, the lost revenue in farmable areas near the wetland due to lower yields. And so in this case, you see in the survey included almost 600 or just over 600 respondents, almost equivalently over Alberta, Saskatchewan, and Manitoba. And about 22 to almost 30% of the respondents acknowledge that they have drained wetlands on their farm. If we look at what the potential consequences to draining this wetlands, the survey asked the respondents, have they been able to report negative effects with their neighbors? And so how do the neighbors of property that a landowner has drained a wetland felt about the impact of that? And so again, Alberta, Saskatchewan, and Manitoba, this is on a log scale. And I just want to point that out for emphasis. By and large, most of the neighbors reported not having any negative impacts. And those that did reported having downstream flooding, as well as loss of wildlife habitat, as well as other factors that I don't have knowledge of. And you can ask John or Pat about that. But the key thing here is that nobody's talking about the carbon here. And we're talking about the hydrological regulation, the biodiversity. We're not talking about water improvements that wetlands provide, and we're not talking about the carbon benefits. So I just want to point that part out. And so then the survey also asked the farmers, why do you retain wetlands? And interestingly enough, it is also for economic reasons. Wetland areas are unsuitable for farming because otherwise they would be farmed. The wetland drainage is too costly. But there was another reason, and that is that wetlands provide essential ecosystem services, but the ones listed were not the carbon ones. And so I think there's a real opportunity there. So then the question is, can we incentivize the protection and restoration of wetlands for carbon benefit? So I showed you before the drainage rates in number and area. This is just the number of wetlands that have been drained over that 30-year period. And I just wanted to see, hypothetically, what could be a carbon benefit to either protect or to restore wetlands. And so here I want to show you, and as many of you who are out in the field and on the land know, most drained wetlands are relatively easy to restore. It still costs money, but involves plugging the drainage ditch. And so what are the kinds of wetlands that could be restored? Typically class 1 to 3, and potentially some class 4 are on private land. For class 5, which definitely includes permanent and would be owned by the government of Alberta, farmers could receive incentives based on A, if they avoid conversion, in which case they would need to demonstrate the wetland is at risk, or B, if they can manage their wetlands to reduce greenhouse gas emissions. And so some of the work done by Matt Bogard, who's from Lethbridge University, and this result here shows the importance of the upland land use on that wetland. In this case, this is for methane fluxes, much higher in wetlands embedded in a cropped versus a perennial land. And so I just quickly want to go through what some of the benefits could be, and this is the back of the envelope calculation. If we looked at the mean carbon sequestration rate, which I provided you before, 0.6 to 8 megagrams carbon per hectare per year, the time period, 2021 to 2050, the cost of restoring, these are estimates that are based on knowledge that was given to us of people doing the restoration, as well as calculating the cost-benefit ratio. And for the benefit-cost ratio, if the ratio is 1, you get break even in terms of the benefits and costs. But if the ratio is greater than 1, the wetland restoration project is justified just based on carbon benefits. And so I just really want to show you the two key findings. Number 1, with the benefit cost ratio, protection above that 1, restoration below, but also above, but not as high as protection. First finding is you better to protect than to restore wetlands based on that carbon benefit. But where we can look at restoration, the carbon benefits alone may not be enough to restore, and we have to look at some of the other ecosystem benefits. And so this is the final piece that I want to share with you, that there are many benefits that wetlands provide, and we want to explore the synergies between carbon and other ecosystem benefits. And so in that practical tool for estimating the wetland carbon benefit, we are also now expanding that to look at the ecosystem benefit, the hydrologic health, the water purification, the biodiversity, as well as the net carbon sequestration at multiple scales so that they could potentially be used both in a planning context and a regulatory context. And so just taking you back to my key message that I started with, wetlands play a pivotal role as natural climate solutions, contributing to carbon sequestration and greenhouse gas emission reductions. Their protection and restoration are crucial for Canada to meet its Paris Agreement targets, and our scientific efforts will continue to work to getting them integrated into greenhouse gas inventory reporting by addressing the uncertainties, but also developing practical tools that government, industry, not-for-profit, and communities can use. Thank you very much for listening. And if anybody has feedback they want to provide me, I offer you my email address. We are definitely in the model of continuous improvement of our research and welcome any and all comments.
Thank you so much, Dr. Creed, for all of the insights and information that you've shared with us today. And thanks to everyone for joining our science seminar today. Just as a reminder, our next science seminar will be on Tuesday, December the 3rd, with Dr. Andy Crosby from the University of Alberta, who will be presenting on the domains of scale and cumulative effects of the energy sector development on boreal birds. Again, if you're not on our mailing list and would like to be added, please contact our office, the Office of the Chief Scientist, at epa.ocs@gov.ab.ca. So we'll end here today, but again, thanks so much, Dr. Creed, for making time in your busy schedule to share your very interesting and relevant work with us. And finally, thanks to all of you for tuning in today. So have a great remainder of your afternoon, and thanks so much, folks. Have a good day.